So we're very happy to have Gary telling us why Stephen and he did not discover the gravitational memory effect.
Okay, well, I'd like to thank the organizers for giving me this opportunity to talk about the celebration, rather, of 75 years of Stephen's life. We're hoping there'll be many more. And I want to bring together a very early part of his career and a very late part of his career. And in terms of this meeting, I will be harking back to the talk given by Bruce Allen and to the future, the talk which we're about to hear from Andy Strominger. Oops, what's going on here? Okay, the talk is based in part on my thesis work with Stephen, which was described in part by Bruce, and some work over the years with some colleagues, Christian Duval, Peter Horvath, and Pengming Zhang, much of it carried out over the past 4 years at Tours in France. Now, the basic framework of the work we've been doing in Tours goes under the heading Classical and Quantum Space-Time and its Symmetries, and that will play a big role in what comes. But as far as this talk is concerned, an important contribution was made by Shaha Hada over a coffee conversation, which tells you how important it is to have coffee, even if you don't like it. The talk's going to fall into 3 parts: a recollection of my first paper written with Stephen on the detection of gravitational waves using bar detectors. Important point to remember that it was a bar detector. I will try to be brief and introduce you to something many of you won't know, the Carroll group. And the reason for doing that in the present context is that it has an application to plane gravitational waves and the gravitational memory and its relation to the soft graviton. So the end is to try and puzzle out, at least for my own satisfaction, whether the notion of a soft graviton makes sense, or at least whether you can describe it in a coherent mathematical way. I will not be considering in detail the BMS group. I leave that to Andy. But the basic idea is a source which is emitting gravitational waves will emit them so that at large distances you can approximate by a plane wave, which has high symmetry, and you can do a lot of calculations in that case. So that's the basic plan. This is a bar detector, and this is the guy who first built one. The important point here is that it's a bar, it's an elastic bar made of aluminium. It's got piezoelectric detectors there which detect the strain. It's hung in a vacuum. You take the output and you analyze it. So we need an equation to govern it, and these are the equations that we used in our paper, which are hardly original. Basically, the thing I did learn in the physics department here is everything is a simple harmonic oscillator. This is a simple harmonic oscillator. X is the displacement of the bar. The thing on the right-hand side is the forcing term. It's the Riemann tensor. And it's a resonant bar, but it has damping, and Q is what's called the damping factor. In Joe's case, this was about 10 to the 4, which meant if you hit it, it would ring for 10 to the 4 cycles, and if you tried to pump it up, it would take you 10 to the 4 cycles. The resonant frequency was about 1,000 hertz, so this was not very good at receiving impulses or detecting impulses. He had built it supposing the relevant source was something like a binary going around, so there was a resonance he could make use of. Now, the Riemann tensor in linear theory is given by the rate of change, or the fourth derivative, in fact, of the quadrupole moment of the source. So this is quite an important equation here, and it's just the standard thing that you get in the textbooks. Now, we made an observation, it was largely Stephen's if I remember correctly, that this formula is quite useful for extracting information about the signal. The type of signals we had in mind were gravitational collapse because that was the only plausible signal that could have given the extraordinarily large amounts of energy from the galactic center, which Joe was claiming. So you'd like to know if it was that, or perhaps what we now call a flyby. And so we suggested it would be interesting to do the following: integrate this equation 3 times. If you integrate this equation 3 times, you see that, excuse me, I should be, you see that you'll get the first derivative of the quadrupole moment, and if it's initially static and finally static, or not varying, then that integral should vanish. So that's 3 times you have to integrate. On the other hand, if it were a flyby, you wouldn't expect that. You might expect 1 integral to vanish. And it will turn out that it's, for the memory effects, quite interesting if 2 integrals vanish. So that was something that cropped up a little bit, and people talked about it. Actually, we gave the wrong idea about this because we gave an example. Now, here I'm going to use the technology of yesteryear, if I can get it to work. Jim Hartle mentioned transparencies, but this goes back way beyond that. If you wanted to give a talk with illustrations, what you had to do, I hope I can get this to work. There we go. Oh, that's Stephen. We'll come back to that one. You prepare this kind of stuff. So these are the circuits, right? And I was uniquely qualified, since the only person in DAMP who'd actually had to think about circuits as an undergraduate was myself. And Stephen. We used the same textbook, even though we went to a different university. Okay, so this is what you did. Everything had to have impedance. That was the main message of the undergraduate course. And we had impedance. Now, Peter Aplin had visited, and he said, well, this system of Joe's is not optimized. We were going to put these, one should put the piezo transducers between a split bar, and that way it was tightly coupled to a pulse-like signal. And then finally we said, well, these were the 2 types of signals you might encounter. This one, for example, has 1 crossing, this has 3. That was a bad way of putting it because, in fact, it has at least 3, but it could have many crossings. And so actually people misunderstood that, people like Remo Ruffini, and said, oh, but my signal, which is well given by linear theory, even at that time, has many oscillations. Okay, so this I basically forgot about for quite a while until with the discovery of the gravitational wave source in September or so of 2015, became clear that in principle, maybe this was relevant for LIGO. It's probably not relevant for LIGO, but it may be relevant for LISA for a reason I'll explain later, and is relevant to the answer to the question I am posing. Okay, well, a little while later, Zeldovich and Polnareff were considering likely signals from a dense cluster of massive stars or collapsed objects. And right at the end of their paper, they noted, now I thought I had a quote of this, but yeah, maybe I do. Anyhow, that once the signal has passed, this is the metric perturbation in transverse traceless gauge, it would satisfy this equation here, which is a consequence basically of the fact that the Riemann tensor is the second derivative of Hij. Now the solution of this is obviously, even to an undergraduate who'd only read physics, which is that Hij will be linear in time. There are 2 constants of integration in this equation, and generically it should be time dependent. This will become important later. I never knew about this until very recently. I didn't read this paper because I decided that using Bayesian reasoning, that this field was such that they would not detect gravitational waves before my retirement. Now, I retired in 2013, so I was spot on. It's the best prediction I've ever made in physics. Okay, so what they stated is, in the last paragraph of their paper, another non-resonance type of detector is possible, consisting of 2 non-interacting bodies, such as satellites. So this was years before people had dreamed of LISA. I don't know if it's the first suggestion that something like LISA would work. The values of Hij after the encounter of the two objects differ from the values before the encounter, and as a result, the distance between a pair of free bodies should change. And in principle, this effect might possibly serve as a non-resonance detector. One should note that although the distance between the free bodies will change, their relative velocity will actually become vanishingly small as the flyby event concludes. Actually, they didn't say that the distance would permanently change. I'll come to that later. So here are our two heroes. Zeldovich is sadly dead, but this chap, Polnareff, is alive and kicking in Queen Mary College. Subsequently, Brzezinski and Grischuk dubbed this the memory effect in this paper, which dates from '85. The paper of Polnareff and Zeldovich dates from '74, which is 2 years after our published paper with that signal there. And I don't think they were aware of our paper, possibly because of the political situation at the time. Here's Brzezinski, sadly deceased, this, I think last year, and this is Leo Grischuk. I'm sorry for the quality of these guys. And that's Kip Thorne, who also wrote about this effect. Okay, so that's basically the memory effect, and I'll come back to it at the end of the talk. Now, I'll say something very brief about the Carroll group, because it's really more technical than is needed for what I want to say. But basically, we've been looking at non-Einsteinian relativity principles. We heard how inspiring that was from Brian Cox's talk. And we usually think of Galileo and the Galilean relativity principle. And we also obviously think about special relativity. But there's another relativity which is associated with the name of Carroll. And this cropped up in a classic paper by Bacri and Lévy-Leblanc, who found all algebras containing rotations, spatial and temporal translations. They started, and also boosts. And they started with the obvious brackets and then tried to complete them to make a Lie algebra by imposing the Jacobi identities. So you come up with 6 possibilities, and this is very much like the classic case of trying to find the possible geometries of space by just trying to find the groups that can act simply transitively and with rotations on a 3-manifold, which we use in cosmology. The groups are all contractions of the de Sitter group. There's one called the Newton hook, which is valid for non-relativistic systems with a cosmological constant. We all know about the Poincaré group, which is when lambda goes to 0, the cosmological constant. We all know about the Galileo group, which is when lambda goes to 0 and c goes to infinity. And the last possibility here is basically lambda goes to 0 and c goes to 0. And there's a certain duality between these two groups, which is quite nice. We know that we have the light cone. To get to Galileo, we spread that out, so we have instantaneous propagation, but you could close it up and you get no propagation. And now this is associated with approximations one makes, which are so-called ultralocal and forbid propagation. An example of that is the BKL scheme for looking at the behavior of singularities near in cosmology. Now, all these groups have a flat invariant model space-time. This is, of course, for the Galileo group, Newton-Cartan space-time, which will be familiar to many people with its notion of absolute time. Or for Carroll, it's a case where, well, here's the duality. You see, Galilean space-time has a degenerate cometric, and Carrollian space-time has a degenerate metric, and you can see that from the obvious formulae, which is that, oh, excuse me. Yeah, you see, if you take this limit for the contravariant metric and take c to infinity, you get a sensible limit. If you take the covariant metric and take c to 0, you get a sensible limit. And the key point is, this is what you get on a null hypersurface. So you're all familiar with that. because there's one direction, the null generators, which don't cost you any distance in with respect to this. Okay. Now, another aspect of this theory is that the isometries of this, if you just say what leaves that invariant, are not finite dimensional, they are infinite dimensional. And this is the version of the BMS group, so it has some relevance to the considerations of Andy. Now, I'm in a hurry, but I can't resist the following. Well, this is technically what the boosts are like for Galileo, and for Carroll you get these boosts which do the opposite. And there are two times here really, which is this time here, as I'll explain, is the Galilean time, and S is the Carrollian time. So why is it Carroll? Well, it's because of this chap, and there's a quote I have to give. Okay, here we go. Now, I've brought the most essential book for all theoretical physicists other than Hawking Ellis in the traditions of many speakers. It's the collected works of Lewis Carroll, and, well, I won't read out the things in detail from this book, but, well, in our country, said Alice, still panting a little, you generally get to somewhere else if you run very fast for a long time, as we've been doing. A slow sort of country, said the Queen. Now here you see it takes all the running time you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast. Okay, so that's the... People should read that. It's astonishing ideas which are very relevant for not just this case. Anyhow, one way to see this is in higher dimensions. These kinematic groups can be thought of as subgroups of space-time in 4+1, Lorentzian space-time in 4+1 dimensions. You all know about Kaluza-Klein, so you get the Poincare group by going down on a space-like vector, or a space-like direction. Newton-Cartan corresponds to going on a null direction, and Carrollian space-time arises when you pull back the metric to a null hyperplane. A typical null surface is, hint, this is for later, like future null infinity. So I'll briefly, and it has to be brief, I don't know how long I've got here. Yeah, well, here's how you construct it, and the group that leaves invariant the null translations down is the Bargmann group, which is the central extension of the Galilean group, and here is Bargmann. I'm 4 steps from Einstein, and step number 1 from Einstein is Bargmann, and then it goes to Girardello and Ferrara. That's not special. If you look it up, you'll find everyone in this room is no more than 5 steps, I think. Check it out. It's worth a bottle of beer if you can. Okay, so here's how you see what's going on if you were to take a massless field in 5 dimensions and make this ansatz, which is the fact that it's oscillating along the null direction. And then there's this function, you get the Schrödinger equation. So that's the bottom line of this. Now, that was already too fast, so I'll just say you can write down non-standard Carrollian structures, and you take the real line, which is your null generator, if you like. You take a spatial metric, and 2 important cases are the Virasoro group, if you take the circle, and the BMS group, if you take the sphere. So that's all I want to say about that. That's the background. They have lots of applications, but I don't think I really have too much time to talk about that now. Now, I want to talk about Carroll symmetry of plane gravitational waves and this soft memory effect. So what are plane gravitational waves? They are exact vacuum metrics of the Einstein equations with a covariantly constant null killing vector, and they admit a 5-dimensional group acting on null hypersurfaces, the surfaces of constant retarded time. This isometry group, which is 5-dimensional, is a 5-dimensional subgroup, in fact, of the 2-dimensional Carroll group, the Carroll group associated with a transverse space. And what breaks the group down is that gravitational waves are polarized, so you can't rotate in that transverse direction, and so you lose the SO2 that would come in. They're not globally hyperbolic, so Michaelis might not like them, but they're nevertheless useful as a model of plane electromagnetic waves, for example. There's an analog. These have as much symmetry as the standard plane waves that you use in E&M. They have many remarkable properties, emit covariantly constant spinor fields, so they're BPS, big buzzword. All invariants constructed from them vanish. They suffer no quantum corrections. They're exact solutions of string theory. So everybody should know about these, regardless of what part of physics you work in. And here they are. There are two coordinate systems. The first is the form up here. And the main point about these are that you choose the profile of your gravitational wave arbitrarily. That's just a symmetric trace-free tensor. So there are no equations to solve, which makes them very useful to use. And moreover, you can superpose them because it's no equation is like, well, it's a trace k equals 0, of course, but no equation means you can just add up the things. On the other hand, that doesn't reveal the full symmetry. There's a three-dimensional subgroup of the isometry group which commutes, and another way to write them is in so-called Baldwin-Jeffrey-Rosen coordinates, because it was first done by Baldwin and Jeffrey in the 20s, and everybody calls it Rosen coordinates. The main point here is that here are the transverse directions. These are two light-like directions, x plus and x minus if you're a string theorist. And to get from one to the other, there's a coordinate transformation for which you have to solve for this matrix P of u. U is like retarded time. And once you've solved for P in terms of K, A is P transpose P, and all the equations are written down here. You have to impose this condition as well. Now, Kij is just the Riemann tensor. It's just a signal that you're measuring, and it's related to the A by this messy equation. And so, for example, even in flat space, there's a non-trivial solution for B, and thus for A, which is given by this formula. And so that means that Aij doesn't have to be delta Ij in order to have a solution. And if you have a flat solution, P is a diffeomorphism which takes you to the Brinkmann form. Now, in the Brinkmann form, you will notice that if Kij is 0, which is flat, it's globally flat Minkowski space. So that's the maths you need to know. By the way, you can't superpose these solutions here if you use the wrong coordinates. So the principle of superposition for these waves is a coordinate-dependent thing. And the second point is that if you want to get back to linear theory, Aij is delta Ij plus Hij. So here I've said a lot of that. Now the main thing for our purposes is if you have a gravitational wave detector which is looking at freely falling particles, such as Lisa may or will, then you solve for freely falling particles. It's easy, and the basic equation is this, where this is a conserved quantity. That's telling you that if the particles start off at rest before the wave comes, then they will remain at rest in what are moving coordinates. So it's easy to find the motion of the detector. We're going to consider a so-called sandwich wave, where there's a before zone and an after zone and something non-trivial. And so this wave comes in and hits Lisa, and afterwards we observe Lisa. Now this is perfectly flat, perfectly flat. So what memory is there of what has happened? Well, it's all in the coordinates. Because Baldwin-Jeffrey coordinates are constant before and after the wave has passed, you might think, well, what can we say? The positions of the satellites are constant in those coordinates, but if you were to start with Aij being delta Ij, which would be one coordinate choice, Aij afterwards will vary with time in a very prescribed fashion. And so even if you've gone to sleep and failed to observe what was happening during the wave's passing, afterwards you could hope to resurrect some of the information by observing how the particles are moving afterwards. This is the key to understanding the gravitational memory effect. You resurrect the information after the wave has passed past you. There's an issue of how much information will be there. Now, sometimes people say this in a stupid and inaccurate form by saying there's a permanent change of space-time after the wave has passed. That's not true. Space-time is the same as it always was. It's just you're looking at it in a dodgy coordinate system. Is there physics in that? I don't know. You can look at this from the optical point of view. If you like optics, any metric can be given the form of a you could solve Maxwell's equations as if it was in a funny medium, and you can work out the permittivity and permeability of this medium. So, but you've got to use the right coordinates, because the permittivity and permeability of flat space in flat space coordinates is just delta ij. Okay. So, now after the wave has passed, however, there is a coordinate transformation, which you can look up in our paper, which brings the metric exactly to canonical flat form. So what's going on here? Well, one thing you can say is that this coordinate transformation does not tend to the identity at spatial infinity. So if you read all the gauge theory books, that's telling you something, that these are different states. They're soft photon or graviton or Yang-Mills states in that sense of the word. They're zero energy, but nevertheless, you'd like to distinguish between states which differ by gauge transformations which don't tend to the identity at infinity. So that's where you register, or you would like to register, the information after the wave has passed. Okay, so that's basically the story. Now, I want to turn to the question that I posed at the beginning, and that is the following. Why didn't we discover that? Now, there are lots of reasons why. The first is we were just too stupid, but with Stephen on the team, that's impossible. A slightly more plausible guy is that we were considering bar detectors, and the Polnareff-Zeldovich analysis clearly doesn't apply, because there are other terms in the equation. It is true that you can resurrect after the effect, after the event, what hit the bar detector, but it's not quite the same problem as Zeldovich and Polnareff were looking at. But what is true is that however you try to resurrect that information, you will come across these iterated integrals of the Riemann tensor. So the good thing is that we said concentrate on the iterated integrals of the Riemann tensor. They are the key things in which you encode the information. In fact, if you were in the situation that hij was constant afterwards, then in fact two integrals of the Riemann tensor should vanish, and two iterated integrals should vanish, and that appears somewhere in one of Kip Thorne's papers, I think the one with Roginski. Okay, so we can't be blamed for not dreaming up interferometer detectors. That was due to Ron Drever, and even less satellite detectors. So I think we are blameless at that point, but it could have contributed to the lapse. Another thing we might have said, we didn't say, is that if we were using linear theory, it was an unconvincing argument. And you could also say there's no such effect. Now, the bottom line is these two bullet points are, although not necessarily an explanation for why we didn't think of it, but they're also true. It's clearly a linear effect, as they described, but is there such an effect? Now, the vanishing of the Ricci tensor leads to this exact solution. And this is a form of Raychard-Hurry's standard method. Well, this could be equal to when you take the trace. You see the trace of that matrix I had earlier goes out. And this is a form of the Raychard-Hurry equation. Here is Mr. Raychard-Hurry. And in the strict sense, we found it very difficult by numerically plotting. And you can see that it can't be the case that if you start with the things at rest, you can't get them at rest because of the gravitational focusing effect. It may be very weak, but nevertheless, it's there. So in the strict sense of the word, it isn't possible. The effect doesn't exist. And that was pointed out also in papers lately of Felix Pirani sadly died, and Bondi died some time ago, founders of the whole theory here. So that's one explanation of why we didn't discover it, and I find that very comforting. I can't be blamed, I think, for not discovering an effect which isn't there. It's slightly specious arguments, of course, because in practice, the effect could be very weak, and the time it takes for the focusing to take place could be very long. And indeed, this is an active area of investigation by people who work on, mainly on LISA. It's very tricky for LIGO, as I'm sure Bruce would agree. So I'm more or less going to bring my talk to an end now. I just want to show one more of these slides. I think I accidentally showed it earlier. Let's see where I can find it. It's a little bit vague, so dark, so I want to turn down the lighting. Oh, this is Stephen. It's a bit better. We're flying in some plane. I think we were crossing the Atlantic. And I'd like to make a few comments about Stephen in the last few moments. In fact, how many moments have I got? That's fine. Okay. So I just want to say that Stephen has been an enormous inspiration to me, and he's given me great support. Most people get a bit despondent when things go wrong, but he's always been able to encourage me. And I want to say something else about Stephen, which is a sort of personal experience. When I came up to this university, I wandered around the little museum that the Cavendish had, looking at the photographs of the graduate students under J.J. Thompson. And I'm looking at all these names, and I realize I recognize every one of them. They're in the textbooks. So I got a little bit sad. I thought, well, you know, this is going to be tough. And, but, you know, like most students, you go to the lectures, which are usually pretty bad, and so you feel a bit better. And by and large, you have the impression that it's not impossible that, you know, it's like any human activity. You think, well, this person, if I really tried, I could do that. It's imaginable. But occasionally, as with Mozart and the guy who, I've forgotten the name, but you probably know the film Amadeus, you encounter people which you just cannot imagine emulating. And the first person that I found in the university, and I was very fortunate, was Stephen. Already at that time, he was universally regarded as the cleverest guy in the maths faculty. He'd made amazing contributions, and at the same time had been facing disaster in his life, and he still persisted. The other thing I learned from him, which I feel is very important, is that he was the embodiment of the motto of the Royal Society, which, if you know, is nullius in verbo, take nobody's word for it. He wouldn't take anybody's word for it. He was stubborn and awkward. But he also persisted in every endeavor in insisting what the founders of that society insisted they were about, which was to test whatever the idea was against experiment. He continues to do that, and I think that's a fantastic achievement. So I'd like to conclude with that point. Thank you for your attention. Just in case you are interested, there's a whole bunch of papers here which give all the details of what I've just been saying, including one which just came out, well, the revised version of the one that just, one of these papers just came out this morning, which is a short, I hope, snappy introduction to what we were trying to do.
Questions?
Steve?
You didn't identify the last portrait.
Oh, I'm sorry. Let's have a look at that. You don't know? That's Hermann Bondi. You know how he used to demonstrate gravitational waves? He was a big man. And if you'd asked him about the memory effect, he'd probably say something like, I think I identified all the rest, but I'm not. And, you know, sadly, they're not with us.
Gary, I wasn't quite clear.
Yeah.
I wasn't quite clear at the end of your talk whether you were saying that there was a real physical effect or not.
Well, there is. There
Yes,
is. The
yes.
physical effect is that things will, in general, move afterwards.
Yes.
And you get two pieces of information, roughly speaking, which you can deduce something about what has passed. So there's certainly that physical effect. But what won't happen in general, as an exact statement, is that they will be at rest before and after.
Yeah, so actually this is something I've been looking at recently, using the Brinkman gauge, where it's very clear what's happening because you just get motion of the geodesics, and they act as though, the particles act as though a force is acting on them,
exactly.
and you don't have to worry about the geometry because in that plane the geometry is just standard. And so you can see from that when the wave passes by, you get a velocity effect afterwards, and so they have a net velocity. And so velocity memory does seem to be a real effect.
Exactly. No, I entirely agree.
Yes,
Yeah.
okay.
Yeah, we did it both ways. You can translate using his P matrix. Pengming Zhang has produced enormous numbers of plots of this sort of thing, which are in our papers. You're absolutely right. It's just that it's so much easier to explain what's going on, for me, in the Brinkman coordinates. And they're intimately, Baldwin-Jeffrey-Rosen coordinates. And it's so much closer to the notion which will be talked about, I think, by Andy, of the soft graviton. The soft gravitons, from this point of view, are just vacuum plane waves, which are flat, but described in dodgy coordinates. Okay.
I'm trying hard to find something to disagree with, but can't we separate the displacement from the velocity effect by just going to arbitrarily large radius? So I think in an expansion in 1 over r,
well, I should say this is strictly a plane wave approximation. If you were to take into account the decreasing amplitude and so forth, then indeed you would get corrections. What I'm saying is if you're at finite distance from a source, you are to some extent well approximated and you're entitled to use a plane wave approximation, just as we do in E&M. But it won't capture the whole global behavior around the sphere. What we think, however, is it does capture, but this is for the future, a version of the BMS group. I mean, the Carroll group, which is at the basis of why we could solve the equations, has a VMS extension, and it would be interesting to do that, but we've not yet checked that out in detail. So the VMS group you normally talk about is all the way around the sphere.
Right. So I definitely completely agree with your statement that the gravitational memory is not encoded in the space-time itself, but only in the test.
Yeah, well, this is an unfortunate misapprehension in some quarters.
And Massimo Parati and I made a similar point recently, but more importantly in that paper we conjectured something that you just confirmed, which is that in theoretical physics discoveries are always known by the last person who discovered them.